Okay, so in this video we continue with subtopic 5.2 induced EMF. Okay, yesterday in previous video we discussed about Faraday's and Lenz's law. In this video we will discuss about specific calculation for the induced EMF for specific cases. Okay, so we start with a coil. Okay, case like a coil here. Let's say if I have a coil sitting on a plane. Okay, and then according to Faraday's law, you know that induced EMF equals to negative dV over dt, and from subtopic 1 you know that phi is equals to BA cos theta. So if any of these quantities like B, A or theta changes, then you expect to have induced EMF. And if theta changes, then that means the coil will start to rotate. Okay, that one we'll discuss a little bit later. But now we want to focus what happened when B and A changes first. So normally the question will ask what will happen if one of these quantity changes. Okay, let's see if we want to discuss about B first. So if B changing, that means maybe you can have increase in magnetic field. So example, this is my B initial. Okay, so for B final, let's say if the quantity of magnetic field increase, example, so you expect that the numbers of magnetic field line increases as well. So maybe it's increased like that. Okay, so here this one is my B final, where B final is bigger than B initial. So if my quantity of magnetic field changes, from this equation A and theta remain constant for this case now. The only thing that is changing is B. So I can write down the formula epsilon equals to negative A cos theta multiplied with dB over dt. So dB dt is basically change in magnetic field with respect to time. Okay, so I can write down dB over dt as B final minus B initial, and delta dt is equals to delta t, total time taken, and then how much change the magnetic field happens. So here is delta t, the time taken from B initial to B final. So it should be final minus initial. Okay, and again, if you want to determine the direction, you have to use your Lenz's law, where we try to oppose. So in this case, let's see if you want to do it, you can expect that the knot is going into the page initially, right? So if you want to change, because now the magnetic field increase, you want to oppose those. So basically you want to put your thumb in opposite direction, which is going out of the page, and you expect that the induced current will be in that direction. Okay, that one is what will happen if the magnitude of magnetic field changes. Okay, so this time I want to focus on the magnitude, because yesterday or previous video we discussed about changes in area. We discussed about the direction. Okay, now we want to discuss what will happen if the quantity that is changing is actually your area. Okay, example over here you have B, so the B doesn't change, magnetic field constant, but the one that is changing is the area itself, area of the circular coil. So maybe it becomes a little bit bigger or a little bit smaller. Okay, let's see if I make it a little bit smaller. So you can see that here, this one is my A initial, oops, this one is my A final, and in this case my A initial is smaller than A final. Okay, so this is the magnitude, this is the quantity that is changing. So from Faraday's law, again, you know that d over dt phi, which is b a cos theta, don't forget to put the negative. So I can factorize everything other than a, so it become negative b cos theta. In this case, theta is 90 degrees, right? Sorry, theta is 0 degrees, so cos 0 is 1 in this case, dA over dt. Then I can write down A final minus A initial divided by the time taken for this event to occur. So basically you have to calculate the initial area and then final area, then just minus final minus the initial area. Okay, you solve this one and then you simply solve everything. So then you can find the epsilon. So if let's say the question want you to find the induced current, so you need to know the resistance inside this coil. So let's say the resistance here is 100, and then you can apply the Ohm's law, and then the next step is you have to use V equals to IR, or EMF is equals to IR. Okay, so in general formula, I can conclude that this equation is either becomes epsilon equals to, let's put a line over there and over here. So basically I can write down negative, okay, if the magnetic field is the magnitude that is changing, I can write A cos theta dB over dt. Remember that dB is B final minus B initial, and then if you have more than one loop, basically just have to multiply with numbers of n, right? If the numbers of loop changes, you can also do the same equation. It's just that it becomes dn over dt, okay, and b and a is constant. And then if a is changing, I can write down as negative b cos theta dA over dt, and this one I can put n as well. Okay, so this is the general form that you can use. So basically in equation, you can use this equation straight away. Okay, the next case is for straight conductor moving across a magnetic field. So example over here, if I have my magnetic field going into the page like that, it's a constant B, and then this one is basically a straight conductor that move across the magnetic field. So basically you can see that as it moves, let's say it moves to the right, okay, that this particular coil, this particular straight conductor, we try to make a motion like it cuts off the magnetic field. So you can see that the area that it's covered changes. So initially it has a bigger area, and then it becomes a smaller area in this case, right? So because there's a change in area, basically they will have a change in magnetic flux, and as a result you have a change in you have induced EMF. So you know that from Faraday's law, induced EMF is equals to negative B A cos theta, right? Sorry, dB, I just write it down again. So it should be negative d phi over dt, and becomes negative dB A over cos theta over dt. Okay, and in this example here, you can see that the theta now becomes 90 degrees. Okay, because theta now becomes 0 degrees, so this one becomes 1, so it's always 1, right? So you left with B and A. Okay, obviously the A is not, the B is not changing, so I can bring the B outside, so you can write down as negative B dA over dt. Okay, the area is covered over here, I can write down as L, which is the length of the length of the straight conductor, and dx, this one is the change lah. Okay, the changes that it brings forward or backwards lah. Kalau dia bergerak, then you expect the change of x there. So I can write down here negative b, my dA now becomes L multiplied by dx. Right, this is thus the area here. So length multiplied by the side, L times dx over dt. Okay, so you know that dx over dt is actually equals to velocity, because that one is just the change in displacement over time. You can write down this one as BLV. Okay, so this is the equation, and in the final general form, you can write down as epsilon equals to negative BLV sine theta. Okay, and remember that this theta is angle between B and V, where theta is the angle between B and V. In this case, the V is to the right, the B is going into the page, and this time it becomes sine 90 degrees. So you know that sine 90 degrees is 1 lah in this example. And for the direction, again, you have to use the Lenz's law. Okay, so the negative here indicates the direction lah, the Lenz's law. So basically what you're going to do is that you have to put your thumb in the direction of the V here, and then magnetic field with your 4 fingers, and then because this one is a current direction, you want to determine the direction of the current, you just have to follow the direction of the palm. In this case, current will be pointing upwards on the straight conductor itself. So it becomes something like this, like that, and like that. Okay, so because there's current, there's a resistor, and then you can calculate the voltage across the resistor, which is basically this one lah. Okay, we try a few examples after this, and then maybe we can focus on calculation and direction. Okay, so another cases is when you have a rotating coil. Okay, example over here, if you have, let's say this one is hanging, right, and this coil starts to rotate in that direction and that direction, what will happen is that the angle between A and B will be changing. So initially, let's say it's like this. So initially you can see that the direction is in the same direction. So once it starts to rotate, so the angle changes. And obviously the values of flux changes as well. Okay, because theta is changing. So another example is over here. Okay, maybe this side of view is much easier for you guys to see. Initially in the same direction, A and B. Okay, and then it start to have some angles, and then start to have like a 90 degrees there. Okay, maybe I can bring this one over here, and I can draw this one downwards. Okay, so because there's a change in theta, then it will produce an induced EMF. Okay, sometimes you can simply calculate using the cos theta initial minus cos theta final, but most of the time you have to use the formula here. So you're gonna derive the formula. So you know that epsilon is equals to negative d phi over dt, where phi is BA cos theta. Okay, since B and A does not change at all, so you can write down this one as negative BA. Okay, maybe if you have numbers often, I can put n as well, so I just put it straight away. So this one become negative NBA, d dt cos theta. Okay, since we are dealing about a circular motion, right? So omega, if you guys still remember, the velocity in circular motion is equals to displacement in circular motion over time. So theta here I can replace with omega t, and I can substitute inside this equation there. So now it becomes negative NBA d over dt cos omega t. And because this one is differentiate and you have variables t inside there, so you can differentiate this one. Okay, so cos, if you differentiate, becomes a negative, right? So it becomes negative sign, so you have NBA sine omega t, and you still have to multiply with the omega. So that omega can bring it to the front, so that your equation now becomes NBA omega sine omega t. So this is the general formula that you can use to calculate this situation. Okay, so the summary for this chapter, first you guys learn about Faraday's law and Lenz's law. You know that Faraday's said that induced EMF is directly proportional to dphi over dt, and the negative sign there because of the Lenz's law, where the direction of induced EMF is try to oppose the change in flux. And then you have a straight conductor, a coil, and a rotating coil case. So ada three case now. And for a straight conductor, it is simply BLV sine theta, but remember the theta there is the angle between B and V. And then for a coil, you can have either change in magnetic field or change in area. And then for rotating coil, you have NBA omega sine omega t. So normally if they ask you to find then the maximum EMF, so this one becomes 1, where this one is sine 90 lah, sine 90 degrees. Okay, so let's try to look at some of the example. This one is question number 8 from the tutorial. It says that a magnetic flux of 4 times 10 negative 5 Weber is maintained through a coil for 0.5 seconds. So find the EMF induced in this coil by this flux. So there's no change whatsoever. So because there's no change in flux, you can say that there's no induced EMF. No induced EMF. Okay. Okay, question B says that the magnetic flux linkage to a coil of wire placed through a uniform magnetic field is 0.6 Weber. So linkage, normally we can represent with L symbol there. Okay, this one means that total numbers of flux, including the you already multiply with numbers of n. Okay, if without linkage, normally just for a single coil, the total is 0.6. If the direction of magnetic field is reversed, so basically you can imagine that this is the position of the coil. Okay, the same direction. The only thing that is changing is actually the magnetic field in this case. So initially here, so this is the initial part, this is the final part. Initially theta and B is in the same direction, so I can say that theta is equals to 0. B and A in the same direction, so theta equals to 0. On this case, theta is equals to 180. Okay, you know that if you want to write down as cos theta, so cos theta becomes cos 0, which is 1. This one cos theta becomes cos 180 degree, which is negative 1. So if I want to write down the solution, so I can write down some EMF is equals to negative change in flux, right? Oops. The magnitude is the same, it's just that the direction is changing. Okay, so final is equals to negative 0.6 minus this one is positive. So this is the final, this is the initial, divided by change in time, which is 0.1 second. So negative 1.2 divided by 0.1 is 12, and then it becomes positive 12 volt. So the magnitude of induced EMF is equals to 12 volts. Okay, the next one, a rectangular frame of 30 times 20 centimeters. So let's say this one is 30 times 20. So area is equals to 0.3 multiplied by 0.2. Let's say we calculate that one. 0.06 meter square. Right, with 300 tons of fire, n equals to 300. The coil is situated in a uniform magnetic field where the plane is perpendicular to the field. The plane itself, so this is the plane and this is the field, so it's perpendicular. So B in this direction and A will be in that direction. Okay, it says that calculate the magnitude induced EMF in the coil when the magnetic field change from 0.8 to 0.8 Tesla in 0.96 seconds. So the time taken for those changes is 0.96 seconds. Okay, B initial is equals to 0 Tesla. B final is equal to 0.8 Tesla. So you can calculate this one using summation, EMF, induced EMF is equals to negative NBA cos theta. So because this one adalah theta is equals to 0 degrees, so cos 0 is equals to 1, so I'm not going to write the cos there. So you have B A, I write down the formula first. Okay, theta is equals to 1. The only thing that is changing is the magnetic field, so I can leave the magnetic field on the right hand side. So you're left with negative NA dB over dt, which is basically B final minus B initial. Okay, so negative NA B final minus B initial divided by change in time. So N is equals to 300. Area is 0.06. B final is equals to 0.8. Don't mix up final and initial, or else you get a wrong answer. And then delta T is equals to 0.96. So here I got negative 15. So the negative, you just leave it like that. Okay, don't simply ignore the negative. So for question number 8D, it says that a wire loop of 18 centimeters, so radius is 9 centimeter. That means the area norms from pi r square, which is pi times 0.09 square. I got here 0.025 meters square, the area. Place in uniform magnetic field, B equals to 0.6 Tesla. The plane of the loop is perpendicular to the direction of the magnetic field. So this is the plane and this is perpendicular to the magnetic field. So that means my area to the right, my magnetic field to the right. So theta is equals to 0 degrees. If the loop is quickly removed from the magnetic field, area within 111 meter per second. So delta T is equals to 111 times, millisecond. Calculate the induced EMF. So initially, B initial is equals to 0.6 Tesla. This one is very similar to the previous question. Final is 0 Tesla. So I can use EMF is equals to negative dphi over dt. So the only thing that is changing is the magnetic field. So NA cos theta dB dt, which is B final minus B initial over delta T. Okay, this is a wire loop, so you can say that N is equals to 1. So you have negative 1, area is equals to 0.025 multiplied by cos 0 degrees just now, which is equals to 1. magnetic field final minus initial, so 0 minus 0.6 divided by 111 times 10 negative 3. So that one become positive. And I got here 0.135. Okay, the unit would be in volt. So this is the values for induced EMF. Okay, next question, question number 9a. A rod of length 1.5 meter moves perpendicularly to a uniform magnetic field of 0.7 Tesla at the speed of 25 meter per second. So maybe you can imagine you have a magnetic field going into the page. Okay, and then you have straight conductor moving perpendicular to the field. So maybe this is the conductor and it start to move in this direction. Okay, so the angle there would be between BLV. So you want to solve using BLV sine theta. So a moving straight conductor, this is the formula. The theta here is the angle between B and V. In this case, theta is equals to 90 degrees. So sine 90 is equals to 1. Okay, B is equals to 0.7 Tesla. Length is equals to 1.5 meter. V equals to 25 meter per second. So now you just have to substitute everything. 0.7, 1.5, 25, sine 90 degrees, which is 1. I got here is 26.25. Okay, but then it says that if the resistance of the rod wire is 7 ohm, calculate the magnitude of induced current. Okay, this is the induced EMF. So if you want to calculate induced current, you can use V equals to IR. Okay, this is from Ohm's law, and our induced EMF is our V. So 26.25, just one volt. R equals to 7. So induced current is 3.75 ampere. Okay. What else did they ask? Okay. So next question 9b. An airplane with a wingspan of 60 meter. Oops. So maybe this is the airplane. Maybe you can see like top view, something like that. And it moves across a magnetic field where the downward components, so we focus on downward components of Earth magnetic field. B is equal to 6.0 times 10 negative 5 Tesla. Find the magnitude of induced EMF between the tips of the wing when the speed of the plane is 225. So V is equals to 225 meter per second. Okay. So the length of the the wing is equals to 60 meter. So velocity to the right, magnetic field downwards, into the page. So angle theta is equals to 90 degrees. Again, you want to use the same formula because this is a moving straight conductor across a magnetic field. I mean, the wing should be straight lah. So BLV sine theta, magnetic field 6 times 10 negative 5. Length is equals to 60. V equals to 225 multiplied by sine 90 degrees. So that one is equals to 1. So 6 negative 5, 60 times 225. 0.81 volt. Okay, that was for question 9b. Question number 10a. The coil of generator has a 50 loop and cross-sectional area of 0.25 meter. Calculate the maximum EMF generated by this generator if it is spinning with an angular velocity of 4 radian per second in 2 Tesla magnetic field. So now we are talking about a rotating coil. Okay, so you know that if you want to solve a rotating coil, you can use induced EMF equals to NBA omega sine omega t, right? But it say that they want to calculate the maximum EMF. So Emax, this one becomes 1. Maximum EMF sine omega t or sine theta is equals to 1. So we just focus on this part. Okay, n is given 50 loops. Cross-sectional area A is equals to 0.25. B is equals to 2 Tesla. They give you straight away omega, which is 4 radian per second. Just check the double check the unit. So this one becomes 50 times 2 times 0.25 times 4. Measure omega in SI unit, and sometimes they give you in revolution per minute or revolution per second. So you have to convert those values. So here I got 100 volts. Okay. Next question. Question B. Suppose that you wish to construct a simple AC generator with an output of 12 volt maximum when rotated at 60 Hz. The magnetic field of 0.05 Tesla is available. So it says that B is equals to 0.05. Okay, area is 100 centimeters square, so times 10 negative 4, negative 2 times 2. If I want to convert to meter square, how many turns are needed? So again, it says about the maximum EMF. Okay, so you can straight away use epsilon max equals to NBA omega. Okay, they want to find N. They did give you induced EMF maximum, which is 12 volt. Okay, so you want to find numbers of N. So now you have to solve the omega. Okay, they didn't give you directly the omega, right? But you know that omega is equals to theta over t. Okay, if you are talking about one period, like one complete circle, theta is equals to pi, t is equals to period, right? And I can change 1 over t, which is frequency. So omega is equals to 2 pi f. That one is just a recap. So N B A omega is equals to 2 pi f, and this one becomes 12. So N is equals to I got here 63.66 tons. Okay. So if the question want you to calculate like the minimum numbers of turn, you have to state like 60. I think turns don't have any problems You can leave the answer like this. Okay, question number 11. A 1200 turns core of AC generator area is given. Rotating in a uniform magnetic field of 8 times 10 negative 2. If the magnitude of the maximum induced EMF is 35 volts, calculate the angular speed of the rotating coil. I think this one is very similar. It shouldn't have any problem. This one is max, so we can ignore the sign behind there. So numbers of turn is 1200. Magnetic field 8 times 10 negative 2. Area is 5 times 10 negative 2. They want to find the angular speed. So omega is equals to 7.292. 7.29 unit would be radian per second. Okay.